Hello, everybody. Welcome to your Section 5 Chem Talk. Just to make things clear, nothing from today's video or from the work you're doing today will be on the quiz that you will take on Thursday or Friday this week. So without further ado, make sure you have your green sheet out and open to page 25. We're starting Section 5, Reaction Diagrams and Conservation of Energy. So click that Continue button when you're ready, and we'll get moving. All right, so all chemical reactions either absorb energy or release energy. We have none that have no change in energy. Okay, so that's the number one thing we got to get down. Right. And I think we might be hopping to page 26 right now. So if you can flip to page 26, we'll go through some of these notes. It might not be all in order, but I'll let you know if anything changes. So when we have reactions that release energy, or energy is a product of our reaction, whether in the form of light or heat, we call these exothermic reactions. And one way that I help remember this is, right, heat is exiting, or energy is exiting the reaction, right? Just like exothermic starts with an EX, so does exiting. Okay. These exothermic reactions feel hot to the touch because they are producing energy, oftentimes in the form of heat. Right, so just a little breakdown of what a chemical reaction or chemical equation would look like. We would have our reactants, right, producing our products, and then energy on the product side, right? All right, and then the energy of our reactants is greater than the energy of our products, right? We've had all that stored potential energy in the reactants that produced energy through the chemical reaction, so after everything's done, we don't have little energy left over, right? So knowing that little tidbit is going to be helpful in identifying diagrams as either exothermic or endothermic later. Alrighty. So even though energy is a product, right, that potential energy is stored in the reactants, which is why we have greater energy in the reactants than the products. Alrighty, so it looks like we're going back to page 25 to talk about potential energy. So potential energy, also known as stored energy, in chemistry, this is energy that's stored in the molecules' bonds. So as we break our bonds, energy is released, and we see that in the form of an exothermic reaction. Alrighty. The intermediate, so we'll talk about and label some of these together. So the intermediate is the transition from reactant molecules to product molecules. Right? At this time, old bonds are being broken and new bonds are being formed. So our intermediate would be this point in the graph, the chart right here, that has the most energy, right? A lot's going on right then. That's when all of our chemical changes are occurring. Right, so make sure we label the chart that we have on page 25 as I go through it here. So on the left here, you want to draw the arrow up and down and label this as the potential energy of the reactants. Right, so as you go higher and higher on the y-axis, we are increasing in potential energy. Right? And as we go across, we're getting towards the end of our chemical reaction. So the beginning of our chart would be the reactant side, right? The middle is going to be when the reaction is actually occurring, and the end of our chart is going to be our products, or what's left over after the reaction. All right, so we were just talking about the intermediate when we have old bonds breaking and new bonds forming. So that's going to be labeled right at the middle, right? Usually this will be where the peak of our potential energy is. Okay. So make sure you have those two labeled, and we'll come back and label a couple more in a little bit. So we talked about potential energy in the intermediate. Now we're going to talk about activation energy, and this is the amount of energy needed to start or activate, right, a chemical reaction. So basically, right, in order for this chemical reaction to happen, the energy needed to get over the potential energy hill. And we're looking at this little hill right here. So in order for this reaction to happen, right, and for us to get down to our product side, we need to have enough energy to reach, right, the intermediate. And that's where the activation energy comes from. Okay, so we have potential energy labeled. We have the potential energy of our products, right? That's going to be a new one, so you want to make sure you have that. Right, so reactants on the left, products on the right, just like in our chemical formulas. Right, intermediate in the middle. And activation energy is going to be how much, right, energy we need for this reaction to happen. So we need to go from the potential energy of our reactants and reach the potential energy of our intermediate in order for that to happen. Kind of imagine if we had a big boulder that we had to push up this hill, and we want to get it from over here on the left side of the table to over here on the right side of the table. So in order to get the boulder there, we need to push it up this hill, and once we get to the top, it's going to easily roll back down. Right? That's why we call this the activation energy. It's how much we needed for this reaction to take place. All right. So some more important terms when we're talking about reaction diagrams and conservation of energy is the heat of reaction. This triangle might look familiar to you if you took physics class. That means delta or change in. So this little symbol here literally means change in, and the H stands for heat. So change in heat. This is the amount of thermal energy given off or absorbed in a chemical reaction. Right? So however much it's changing. Basically, this is the difference in potential energy between the reactants and the products. So if we were to subtract our potential energy of our reactants and products, right, that would be our change of heat in the reaction. All right, so let's go back to labeling our chart again on page 25. So everything there we have. And the last thing that we're going to label here is the heat of our reaction, right? And that's going to be the difference between our product potential energy and our reactants potential energy. You can see if we were to subtract this blue line, or subtract the red line into the blue line, we would be left with the purple line. Okay, so that's how we get the heat of our reaction, or how much energy was released, because right, the conservation of energy will tell us shortly that the amount of energy we have before and after the reaction should be equal to each other. All right, so let's see where we are right now. All right. There's not any notes in particular on this slide, but this is going to be a good way to help visualize what's happening here. So as we go across a chemical reaction, right, this is going to measure how much potential energy we have. So if this black arrow is up at the top, we have maximum potential energy. If it's at the bottom, we have very little potential energy. So we're looking at putting hydrogens and oxygens together. So when we have the reactants of just hydrogens and oxygens, we have a decent amount of energy stored in those bonds, right? So we're going to be somewhat in the middle, right? As these new bonds are forming and old bonds are breaking, right, it's a very unstable and chaotic system. This is what we call the intermediate, and this is when we have the most potential energy. So when we see that nice hill on our graph, that's being caused by this. And once we have our products, right, which is water in this case, right, it has less energy stored in the bonds, and we're more stable. So the leftover energy gives off water molecules and kinetic energy. So we would have had some heat produced in this reaction. All right. So one last final double check, make sure we have everything on our graph organized. So we have potential energy of reactants on the left, potential energy of products on the right, potential energy of intermediates in the middle. Our activation energy, or how much energy is needed to start the chemical reaction, is at the top left, right? How much we have to get up that hill. And the change in heat of our reaction, right, is going to be on the far right. It's the difference between the potential energy of our reactants and the potential energy of our products. All right. So over time, it would look like this. If we're doing the same example with the oxygens and the hydrogens, right? Activation energy increases as old bonds breaking, new bonds are forming, and then our energy is the least when we have our products and we are the most stable, right? And this is specifically for an exothermic reaction. Okay. All right, so we're going to talk about the other type of chemical reaction, an endothermic reaction. It's pretty much the opposite of an exothermic reaction. Right, so we said in the beginning, reactions can absorb energy or they can release energy. Exothermics, we're releasing energy. These endothermic reactions are going to be absorbing energy. So these notes will be found on page 26. Okay. So right above the chart on page 26, you can fill in the blanks absorb and endothermic. And when you have an endothermic reaction, they feel cool to the touch. A good example of these would be like an ice pack. If you ever had one of those ice packs that you crack it and then it starts to get colder, that's a good example of an endothermic reaction. So we'll have our reactants plus energy on the reactant side, right, to produce our product. So these reactions would not take place if we did not have this energy to get it started, right? And the energy of our reactants is lower than the energy of our products. All right. I know, again, that sounds a little counterintuitive, but in order for us to get to our products, we need to add energy to our reactants. So that's why we say the reactants have lower energy than the products. All right, so when we're filling out our diagram here, we have the potential energy of our reactants on the left, the potential energy of our products on the right, the potential energy of our intermediate in the middle, our activation energy on the left. It looks like we need a lot more activation energy for endothermic reactions than we do for exothermic reactions. And that would make sense because we have less potential energy in our reactants. And then finally, the heat or change of heat in our reaction is going to be, right, the difference between the potential energy of our products and the potential energy of our reactants. So how much heat did we need for this to take place? Alrighty, so make sure, pause the video if you need to, make sure you have everything filled out here. And we're going to talk a little bit about sources of activation energy. This starts at the bottom of page 26. So our first source of activation energy would be light. A good example of this would be hydrogen peroxide. That's why hydrogen peroxide is always in that dark brown bottles, because we don't want the light to get into it. If you turn to page 27, we'll continue our notes. So other sources of activation energy would be heat, friction, or a spark. All of these can activate a chemical reaction. All right. Another thing that can affect a chemical reaction is what's called a catalyst. Right, now let me move the video here so that you can see how to spell that. Okay. So a catalyst is an element or a molecule that speeds up the reaction. A catalyst is going to lower the activation energy needed. Right. So if we're looking at that hump that we have in the middle, if we add a catalyst, that hump lowers. It's not as hard to start the reaction. Right. So catalysts can be added to speed up some chemical reactions. Right. And in the world of pharmaceuticals, this is a big deal because the faster you can make new products, the more money you can make and the more people you can help. So a catalyst can be added to speed up our reaction. So without a catalyst, you might need a whole bunch of activation energy, but with a catalyst, you need much less. Right? And it speeds us up by lowering that activation energy, like I was just telling you. Big thing to note here is that catalysts do not participate in the chemical reaction. Right? They are not a reactant. All they do is speed it up. They're kind of like a spectator that cheers it on and gets it to move faster. Okay, they are not interacting with any of the atoms or molecules on either the reactant or the product side. Right? So it does not change our reactants or products. And if we were writing a catalyst in a chemical formula, we would put that above the arrow to show that it's not part of the reaction, but it is speeding it up. Alrighty, so let's try this ourselves. I want you to label on your green sheet which one of these charts is an endothermic reaction and which one of them is an exothermic reaction. Alrighty. So we should have a little demo for you in class. A lot of times we like to have you guys do it in the investigate as well. Let me just go through, make sure I'm not missing anything else. Alrighty. So there are a little bit of notes left on page 28. Now, I might not have time to talk through all of those. My video expires in 30 seconds. So I'm going to pull up what the finished version should be, and I want you guys to copy that down. Okay, so energy cannot be created or destroyed. Right, this is what we call the law of conservation of matter. It's going to be the same before and after. So potential energy should be called stored energy, right? And kinetic energy is the energy of movement. Right, so pause that if you need to. Come down to 8 seconds, I'm sorry. So Also, make sure you take a second to label these.